Okay, here we go. It's going to be worth the wait. Okay, so we're talking about multiplying two vectors. Now we're on to cross product. We did dot product last time. So with the numbering system I was using before, this is 5b. Number 5 was multiplying vectors. And this is the cross product. And to do cross product by hand, if you have a vector A, B, C, those are the components, and you cross it with a vector D, E, F, you get an X component of B, F minus C, E. You get a Y component of, in parentheses, A, F minus C, D. But then this whole thing is negative. And then in the Z component, the quantity AE minus BD. There are memory devices for doing this, but you never need to do this by hand. Your calculator does it, so learn how to do it on your calculator. Some TI calculators, what the hell? Okay, some TI calculators have a built-in cross product function. And that function is lowercase CROSS and then capital P. And then the arguments separated by a comma are the vectors, however your calculator does it. So if you have, this is the syntax for a TI-89. Okay. So what I wrote here is the cross product of the vector 1, 0, 0 with the vector 0, 1, 0. What are the magnitudes of those two vectors? The length? 1? Yep. And they're perpendicular, right? One's the x-axis and one's the y-axis. So you should get a cross product with a magnitude of 1. And in this case, you get the z-axis. 0, 0, 1 would be the output. To see how you do the cross product on your calculator, remember the appendices. There are appendices for that text that's in D2L. It has all this stuff for the different TI calculators, also for Wolfram Alpha, for something else too. I don't remember what, but there's a bunch of ways you can do this without ever having to think on your own. Okay, that's our goal. So here are a few things to notice about the cross product. Okay, the first one. Notice that the y-axis always has to be the weird one. That comes up over and over again in matrix and vector calculations. X and Z, the components from the cross product follow a similar pattern. The y-axis just has to be a little different, put its little negative there, and that happens all the time. Second, often this is called the vector product. because the output is a vector. Third, the output vector is always perpendicular to both input vectors. There are a lot of reasons that you would need to do this in different areas of engineering. If you have two vectors and you want to know a vector that's perpendicular to both of them, the easiest way to do it is take the cross product of the two. Physically or whatever, like spatially, any two vectors, if you put them tail to tail, define a plane, and the cross product gives you a vector that's perpendicular to that plane. Fourth, the cross product of two parallel vectors is zero, is the zero vector. Fifth, a right-handed coordinate system, which for our purposes just means any allowable coordinate system. You can do things with left-handed coordinate systems, but it's sort of rare areas of math where that's useful. So basically any coordinate system, CS's coordinate system, has to satisfy these three things. The x-axis crossed with the y-axis is equal to the z-axis. The x-axis crossed with the z-axis is the negative y-axis. That's the y-axis always being the weird one again. And then the y-axis crossed with the z-axis is the x-axis. If those aren't satisfied, then all the math we're doing is going to screw up in the coordinate system you're using. It's not an allowable coordinate system.
Is that just because of like that whole right-handed rule?
The right-hand rule, yep. That is why. Yep. I mean, that's how you can visualize it. I'm not sure if I would say that's why, but yeah, you're thinking about it right. A vector A dotted with a vector B versus a vector B dotted with the vector A. What's the relationship between those answers? They're the same. The order does not matter. With cross product, it does matter. So the last thing is order does matter for cross product. If you take a vector A cross B, that's equal to the negative of B cross A. So any definitions I give you with cross products in them, and we're going to see a lot of cross product, you can't change the order of these things. Any questions about that? Okay, like for the assignment I'm going to give you, you're going to do a bunch of calculations with dot product and cross product and stuff, you're going to want to figure out how to do that on your calculator. Don't do it by hand. Okay. Really, this first assignment is going to be just sort of getting familiar with doing these vector calculations on your calculator. All right, so that's it for multiplying vectors. Now the next thing we want to find is how to calculate a vector that goes from a point A to a point B. And I'm going to usually say that as 2B from A. So be sure you're thinking carefully about which one I'm talking about. So this is the A, here is the start, and the B is the end. There are two ways to do this. The first one is if you are already given the coordinates of these points A and B. So if you know the coordinates, I'll write them as vectors, so A and B. Okay. Coordinates you can always think of as vectors because they're a vector that goes from the origin to the point. So if you know those coordinates, then the vector that goes from A to B is just simply B minus A. So that's easy. If you don't already know the coordinates, of A and B, temporarily imagine that the origin is at the point A, and calculate the coordinates of the point B, and that's the vector going from A to B. So let me show, so I'm not going to show an example of that first way. I mean, that's just subtracting component by component, so that's easy. But the second way, here's what I'm talking about. So here's an example. Let's say that you have a cantilever beam coming out of the wall, and we know that this angle is 30 degrees. And we know that the length of this beam is 0.5 meters. And let's say this is the point A, and this is the point B. So we want to calculate the vector from A to B. Do we already know the coordinates of these 2 points? No. So we're going to imagine the origin at A at the starting point, and then just calculate the coordinates of B. So I'll draw the coordinate system here like this. Then the point B is over here where this is 30 degrees. So what's the counterclockwise angle from the positive x-axis to this line here, this vector?
150.
150, yep, 180 minus 30, so 150. And so that vector D is equal to 0.5 times the cosine of 150, 0.5 times the sine of 150, and that is negative 0.433, positive 0.25. And that's true no matter, even if you'd already defined a coordinate system for this problem, you know, say your coordinate system is actually over here somewhere, you can do this for the calculation. This coordinate system, though, does have to be in the same orientation as whichever one you've defined. Okay. Ooh, my negative disappeared. That's negative. Yeah.
And you do like -0.5 cosine 30.
Yep. Yeah, feel free to do it however it makes sense in your head. You know, I like this just going counterclockwise from the x-axis for two reasons. One, everything's the same, you know, you treat everything the same. And two, it works really well if you're writing programs, you know, because the program can't think about what quadrant you're in, or maybe you could make it do that, but it would be unnecessarily complicated. It just works for everything, so it works well in algorithms.
How do we handle the multiple if we're working a problem where we have to do, you know, two different, whatever, from different areas, but we needed to do arithmetic between those two.
Mm-hmm.
But they were, you know, calculated on different.
Well, you need your coordinate systems, any coordinate systems you're using for calculations together, they need to be the same orientation. And then this is just a case where, I mean, this is just a way to think about it, you know. This is just a way to calculate what that vector is in your coordinate system. It's not like you really moved where the origin is, you're just using this as a way to come up with the answer.
Just like, it was like, you know, organizing to like ideally labeling the coordinate system.
Yeah, that's a good idea, I think, because none of this stuff means anything without being attached to a coordinate system, yeah. Okay, so this was calculating a vector from one point to another point. An extension of that we're going to use all the time, so this is number 7, is calculating a unit vector in a given direction. Did I already do that? I guess that was what I talked about before, was calculating a unit vector in the same direction as a known vector. This one is a lot like that, but there's going to be one other possibility here. So calculate a unit vector in a given direction.
So that kind of serves as the cardinal rows.
As what?
So that kind of serves as the cardinal rows as far as, you know, different sketches of the same system.
The unit vectors? So this is the thing that I said we'll use with cable tensions most often, and with other contact forces. And I'll show you know, when we get to that, I'll try to point it out. But for now, it's just a mathematical thing that we need to know how to do. So there's two ways to calculate this, and largely which one you use is determined by whether you're working in 2D or 3D for the problem you're in. two ways to calculate. The first one is if you're given an angle between the desired vector and some reference line, you're really only going to use this in 2 dimensions. Trying to figure out angles between things in 3D gets super complicated super fast, so there's an easier way to do that in 3D. So for this one, you're going to go, so choose a vector parallel to the reference line, and find the counterclockwise angle theta from the positive x-axis to the reference to that vector you defined. And then second, find the counterclockwise angle phi from the vector defined above to the desired vector. And then your unit vector is just going to be cosine of the quantity theta plus phi, sine of the quantity theta plus phi. That feels pretty abstract, so let me show you how this works. Okay, so let's say that we have a wall, and we know that this wall makes an angle of 50 degrees with the horizontal. And then we have a cable, connected to some object, and then maybe there's another cable there. And we know that this makes an angle of 30 degrees with the wall. Okay. And we want to know a unit vector in the direction of this vector. Okay, so how do we do that? Well, the first step is to choose a vector that's parallel to the wall, because the wall is our reference line, right? It's measuring, we know that this angle is measured relative to the line of this wall. You follow what I'm talking about? Okay, so choose a vector that's parallel to that line. It doesn't matter which way. I'm going to draw a coordinate system. And so this is a vector that's parallel to the wall, right? We know that this is 50 degrees. Okay. Yeah, because all we're dealing with is just the angles, so we don't care what the magnitude is right now. We're just trying to find this angle. So what's a counterclockwise angle from the positive x-axis to that line? What? 130. Yep. So that's what I call theta. You know, theta is equal to positive 130 degrees. And now, I don't know if you remember this from like SATs or whatever, but we know that this is also 30 degrees. So now I'm going to draw a second vector that's 30 degrees this way from the one we drew, right? We know that this is 30. Starting at that first vector, do we go counterclockwise or clockwise to get to our final vector? Counterclockwise. So our phi is positive 30. If it went clockwise, it would be negative 30. And so our unit vector is cosine of 130 plus 30, 160. Sine of 160. And that is negative 0.94, positive 0.342. You can do that in 2D, and a lot of times you'll see problems set up sort of that way where the vector you want is measured against some other reference line. This is the approach you want to take. And it doesn't just have to be 2 steps. You could maybe imagine like you'd have a wall and then a rope and another angle from the rope to a beam and another angle from the beam to something else you want. And you're just adding these angles going, you know, figuring out, how far are you going counterclockwise? How far are you going clockwise? Eventually you get that angle and just use sine and cosine. If you have any questions about that, I feel a little stress coming from this one. I'd be happy to answer any questions right now, but the vector review has this in it, and so you'll. Yeah.
Really quickly, why was the phi angle 30?
Because that second angle is, so this this is just a reference line, right? That's not the one we're looking for.
Right.
And what we're given in this picture, all we want is the counterclockwise angle from the positive x-axis to this one line that's parallel to the cable. But we didn't have that. We just had the angle of this relative to the wall, right? So first we figured out the angle to the wall. Then from the wall, we figured out the angle to the vector we want, add those together, and you get the answer. Yeah, something like that. All right, yes.
And so the vector that unit vector superimposed on that initial drawing.
Yeah.
What is that a force acting on?
That's the direction that the direction of a force that cable would apply to that ball. And we wouldn't know the magnitude yet, but that's something we would calculate using statics. Okay, if you're in 3D, or if you already know the coordinates of the points, at like of a point that you're going from and a point you're going to, then there's this other way. So given 2 points along the vector's path, with known coordinates, and this works in 2D or 3D. So this is pretty much the way you always want to go in 3 dimensions. So like, for example, let's say we have the end of a beam and a cable that connects this beam to a wall. And let's say that we know that the coordinates along this cable are 5, -6, and 7, -5. And we want the unit vector going this direction because that's the direction of a cable force that would be applied to that beam. Well, you can first calculate a vector that goes from 5, -6 to 7, -5. So in which order do I subtract these to get a vector from 5, -6 to 7, -5? Yep, so it's 7, -5 minus 5, -6. And so a vector pointing from that left point to the right point is 2, 1. And now you're just taking a unit vector of this vector that we know. So the formula I gave you before is we're going to divide this by the length. The length of that vector is square root of 2 squared plus 1 squared, so square root of 5. And so you have 1 over square root of 5 times 2, 1, or 2 root 5, 1 root 5. And if you're lucky, your calculator, you have a modeler calculator that does all that stuff for you. If you're not as lucky, you have a different TI calculator. It's very easy to enter a program in that does that stuff for you, and that's also in the appendices. And I would recommend doing that for the programs that are given in the appendices. Okay, any questions about vector calculations? So you read the vector review. I'm going to give you the vector problems to work on. The next thing we're getting into is particle statics. And I sort of hate to stop early because we started late, but I think that is a good place to stop. So that's what I'm going to do. So look on D2L maybe tomorrow morning, and that assignment will be up. And yeah, let me know if you have any questions.
Can you submit it on D2L?
Yes, you'll see that there's a place in D2L that says assignments, I think. And in there, I'll have a folder. It's a subgroup that says daily assignments and a folder that'll say whatever today is, 8/26. And you just put in a photo or a PDF scan of your work. And I'm just, like I said, just looking to make sure you're doing this work, you know? I'm not gonna be grading it or whatever. So if you have questions about something you did, you need to ask me about it or check on the solution to make sure that you're thinking about it right, okay? All right, have a good weekend.
You too.
Thank you.